Hi everybody, welcome. Today I'll speak about out-of-vocabulary word detection that me and my colleagues have done here in Brno. First, a couple of words about motivation. So out-of-vocabulary words are words unseen in training data. In terms of classic ASR, they would mean that they have no entries in the dictionary and the language model, so we have no idea how they look, and thus they cannot be recognized. But they're also usually important. They can be names, addresses, specialized vocabulary, new words that emerge, so we can be really interested in them. Obviously, if you use character or BP generating end-to-end system, they work around that. But in that case, we still don't have any idea when and what these OOVs are, and we might be interested in that for our applications. We define two success metrics for our OOV task, 2 tasks and 2 success metrics. First is the OOV detection, and the task is to find OOV segments in speech and return the start and end times of the OOV segment. And we define true positive if the hypothesis overlaps with the reference for more than half of the reference duration. So there are different methods to do that. You can also do the fuzzy decision on that, but this seems to be what most other people are using, so I wanted to be comparable. The detection recall, thus, is the percentage of true positive in the reference list of OOVs, and detection precision is percentage of true positive in the list of detected OOV occurrences. The second task is OOV recovery, and the task is to recover acoustic and or graphemic representation of the OOVs. So we count the recovered OOV as a true positive if the word's recovered graphemic representation does not differ from some reference word by a Levenshtein distance more than once. So as an example, the word moreover would be okay, but anxious would be not. We made this decision because usually with one Levenshtein distance error, the word is still recognizable for all practical applications. And also, so many things can go wrong with phoneme to grapheme and other stages that we allow ourselves that. With this true positive definition, the recovery recall would be percentage of the OOVs from the reference OOV list that we successfully recovered, and recovery precision would be percentage of the words that we recovered that actually belong to the reference OOV list. Now I'll talk about our detection and recovery pipeline with the beginning with the end-to-end approach. So first, we train the word predicting end-to-end system. So it's trained to predict word labels, and one of those labels is the OOV label. So for the training data, we substitute all OOVs with this OOV label, and we train the system to also predict that as well as other words. The output of that stage is obviously the word labels, and also we can use hidden representation of this OOV system in our detection task. The next stage is OOV detection, and we'll talk about 2 approaches to that, using attention and CTC. We'll talk about it later. The output of that stage would be OOV time region, start and end time, and this is where OOV detection is measured at this stage. Now, as we have the places where OOV happen, we extract phonetic representations for these time periods from phoneme lattices. So we train the phoneme decoder, and I will look at the generated lattices, the lattices generated by the phoneme decoder. We'll look between the start and end time, and we combine together all the possible pronunciations that happen at this time. So the output of that system would be candidates for our OOVs in form of phoneme lattices. Then we do the clustering of the phoneme lattices. We do a version of Chinese restaurant process for that, and that helps us obtain clusters that represent OOV candidates that have more than 1 repeated appearances in our data, and also their most probable pronunciations. Then the next stage would be that we take those clusters, we take one best pronunciation of the cluster, which we believe represents the pronunciation of those OOV words, and we run the phoneme to grapheme system on that to obtain recovered words in their graphemic representations. So that's where recovery is measured. So as you can see, it's a big pipeline, and recovery success depends on a lot of factors, that enough occurrences of the same word are present in the text so we can recover that from the repetitive occurrences, that enough of these occurrences are actually successfully detected, that the clustering worked correctly and assigned enough of these occurrences to the same cluster, and the phoneme to grapheme conversion should work well to correctly discover the good graphemic representation for the word. So a lot of things can go wrong on the road, and actually often do. So in this presentation, we'll focus on detection, and we also show that improved detection also improved recovery. We used two detection methods, and for first one we trained listen attendance spell end-to-end system, which is probably familiar to most of the people here. So it's an end-to-end system which has listener or encoder and speller or decoder, and listener encodes features into hidden representation, and then do you have that? Okay, and then there is the speller mechanism that tries to predict labels, which in our case are words, and also the OOV label for the OOV word. So how do we plan to use that for OOV detection? Is that the attention matrix, if we look at the attention matrix, then for each output label, the attention vector in that matrix is pointing to certain frames that are relevant to the current decision. And our belief that is that if you look for the attention vector for OOV word, it will show us where this OOV word has happened. The next method we used is in a hybrid CTC attention end-to-end architecture, which is probably also familiar to you. And so this system has two decoders with a shared encoder, and the loss is a combined CTC and attention loss, which we can control by weight. And we plan to extract OOV position from the CTC labels, because for each frames we generate CTC labels, which is either word or blank symbol, and we believe that word boundaries are positioned on the frames for which a new label is predicted. A few words on the data. So we chose LibreSpeech because it has good baselines, it's clean speech, there's a big data set. Obviously, we didn't want to beat the current word error rate, but we made sure that our system, if we train it to generate BPEs, is on par with the with some current approaches. So here we compare with 2018 paper, and it works reasonably well. Here we also have baselines for system generating words. So we see that the word error rate is worse because there's more labels. Also, the OOV problem is introduced. So in the system generating words, the word error rate is worse. But if you score it in a way that treats recognizing OOV word as not as an error, but actually as a correctly recovered word, we see that the word error rate goes down, which gives us promise that this end-to-end system actually has good potential for OOV detection. And in the combined CTC and attention system, if you give 0.9 weight to CTC, then we see that the word error rate is a bit worse. But as we'll see later, the word error rate scores do not necessarily translate into better detection scores and vice versa. So a couple more words on the data. There's not enough OOV repetitions in just test data sets, so we split the data differently. We use 600 hours for training and 360 hours for OOV detection and recovery scoring. That gave us more data and repetitions. Also, there's no OOVs in LibreSpeech in traditional sense because it's read books. So first we limited the vocabulary to 10,000 most frequent words for the end-to-end training. And then we also, because we wanted a list of words with more repetitions, we chose a list of 1,000 outdated words for our reference list for recovery. Here's some of the examples. These are not the words that you'll find in normal language model systems, so in normal language models, so we say that we treat them as OOVs. So now that we know about the data and how our detection and recovery work, and before we look at the numbers, let's look at the pictures first. So the first method is determining the position of OOVs from listen, attend, and spell end-to-end system. And here in the picture, you can see for every word label predicted in the system, we can see the attention weights plotted on the time. So on the top, we see the reference sentence transcription with the word boundaries in dotted lines. So we see that although in general the attention goes consequentially in the sentence, we can't really say that it predicts the position of the words that well. So we can say that sometimes the the maximum of attention lies on the boundary, sometimes it's even before the boundary, and some previous paper I cited, they found out that the maximum of attention was in the middle of the word. That's definitely not the behavior that we observed. Then for the other method in the hybrid CTC attention architecture, there's also attention. It's less pronounced because we give less weight to the attention-based decoder and more weight to CTC. But we see in dark black lines are CTC boundaries, and we see that they correspond much better to the actual word boundaries. So the hope is that CTC is much better for predicting where the words are than attention. So now we have the intuition from the pictures. Let's look at the results, the numbers. So the first two lines show the results from the listen, attend, and spell system. Okay. And the last two lines will show results from the hybrid system. So we see that if you look at the attention span, and we only chose the ones longer than 0.5 seconds because that's what makes sense for the recovery. This number of OOV occurrences that we get, and detection, recall, and precisions were not that stellar. And I should mention here that we're mostly caring about recall because if we over-generate OOV candidates, it doesn't hurt us that much because they just won't cluster at later stage. So for us, recall is a much more important measure. So it's not that stellar, but it still somehow works. But if you look at the recovery numbers, then actually it doesn't want to cluster, and the recall and precision are very set. And this is just a cheap and dirty way to check that the problem was indeed in the position of the attention. If we shifted just 0.0 seconds right, then magically there's more clusters and there's better recovery, recall, and precision, which means that usually attention happens actually earlier than the word, and we can't trust its position that well to predict where exactly our word lies. Then the two CTC attention hybrid system, they differ by the weight given to the CTC decoder. So with the CTC decoder half of the weight and attention half of the weight, we see that the detection and that recall and precision of the detection go dramatically up, which we already see in the picture that the borders are much better. And we see also that when we try to cluster the candidates, we get much more cluster, and the recovery and precision go up. So obviously, like recovery, recall, and precision results are worse than detection results, but we already discussed that recovery is a much more difficult task that depends on a lot of things. If you give even more weight to CTC, then even though the number of OOV occurrences stays roughly unchanged, we see that the detection and precision are actually better, and when we look at the recovery results, they're also much better. So even though the system works a bit worse in terms of word error rate, we see that it's much better for OOV detection and also translates into better OOV recovery. Our conclusions then would be that first, end-to-end system works for OOV detection. There is definite potential for OOV detection there. That CTC elements provide better temporal information about OOV positions than attention, and that improved detection results also correlate with better recovery of recurrent OOVs in our pipeline. So improving detection actually helps. Thank you very much for your attention, and it's question time now.
So, please questions.
Yes, thank you for this interesting presentation. One comment, when you defined your evaluation, you were doing this, say, threshold of an edit distance of 1
Yes.
per word. Did you also consider just computing character error rate instead of word error rate? Because the example you gave, like anxious, I mean, you would still say recognize what it means, even if it has an edit distance of 2. So it would be fairly straightforward to also do character error rate when you just include the spaces in between as also symbols.
Yeah, actually that would make more sense, but we wanted to define, is it more like yes or no, have we recognized it or no? As I said, both for detection and recovery, there's different methods to be used. We just wanted one clear yes or no decision, but actually, yes, framing it in character rate would also be a viable decision. There is a bit of a problem with metrics because everybody decides what they want to measure, and hopefully it will standardize soon. So we try to make it in a more clear way that's understandable.
Okay, and I have another question. I mean, with all the end-to-end approaches recently, people are using a lot subword approaches like BPE, which effectively are open vocabulary. So did you, especially like attention approaches, like to use that? And did you do some comparison there by just having a subword unit-based model and see what you get on those words you have never seen in your textual data?
So we actually have baselines for, can I have my presentation back? No?
Yeah.
Okay. Thanks. So we actually have the baseline in byte pair units. Oh, that's a long way. Oh no, it was further. Sorry. So we actually have the baseline in here, I believe. So we actually have the baseline in byte pair units. So if you measure word array, then it's the second line there. So it performs great, and as I mentioned, yes, if you use byte pairs, then you don't have the OOV problem, and it will go away. But yeah, our task was more to discover these new words and see where we can do that in other applications. So, for example, if it's a new product name or some emerging thing, maybe you want to somehow enhance these words further. So our task was not necessarily beat the word array with BPE. But more of discover the OOVs. Yeah, BPs that also solved the OOV problem.
Thank you.
Thank you.
Yeah, okay, we have a question actually from the online audience, from Oleski Zelo from Cyforce. In regard to attention matching the word, okay, I try again. In regard to attention, matching the word location poorly, have you tried repeating the trainings and comparing the attention accuracy? In my experience, the attention is quite unstable and some models can be much luckier with attention to audio matching.
That's actually, that's a good point because as I said, the idea was actually based on one paper that looked at just attention maximums, and they claimed that if they just say that the attention maximum are in the center of the word, they said that it just worked for them, which is definitely what we haven't seen in our model. So yes, maybe differently trained models would have different attentions, but we tried to follow the basic approach that was in the paper so that it's a replicable thing, so that everybody who does the basic listen, attend, and spell would get the same results, and it seems that it's not that reliable for attention.
Mm-hmm. I guess this would mean that you have to train 5 or 6 different libre speech models.
That, we did not do that.
Okay. Yeah.
So do we have more questions?
I think we have time for a quick one. I have a very brief question. So this is kind of a post-processing step. So once you've done the recognition, you rewrite the hypothesis so that you have now OOV words actually with spelling and so on. But so is re-recognizing the same audio with the words added on your agenda, or?
We actually haven't tried this with the end-to-end system, but we tried it when we did OOV decoding in the kind of traditional ASR system in a hybrid approach, in which we took the we added them first to the dictionary with their best phonetic representation, and we ended it to the language model just as unigrams, and I think it improved word array by like 1%. So yes, it definitely seemed to be working. We didn't do that in end-to-end, but we probably should.
Yeah, because it reduces the collateral damage of OOV words.
Yes, but you'll have to also expand the last layer, so I'm not sure how exactly comparable those systems would be. Interesting, yeah, I should try.
Okay.
Thank you.
Okay, so the next presentation will be...
Thank you.
Oh yeah, sorry, yes.